dedicating large IFU observations in this field, ALMA observation, as well as more than 50 hours of imaging from ground-based instruments and HST. Are we good? Okay, thank you. This is not working, but that's okay.
There again, the people online work.
Is it good? Okay. So our survey is really trying to create a mosaic around these 6 quasar fields. We use the F356W GRISM spectroscopy around the field using the reverse GRISM setup. And the argument is that we are creating a 4-pointing mosaic so that the central part of the field has a maximum signal to noise. We also have dual coverage of both the GRISMs so that, if you have contamination from cross dispersion, we can actually recover even single emission line spectra there. The central 70 arc-second or so will give you coverage for the both GRISMs, and the central part is really the deepest part. Within 246 kiloparsec area, we get around 4 times the exposure time than you'd get otherwise. Our goal is really to target between redshift 5.3 and redshift 7 O3 emitters, between redshift 3.7 and 5.1 H-alpha emitters. We also, of course, the setup allows us to get 3-band imaging, which are some of the deepest imaging that you'll get. And in the end, we'll end up with around 110 square arc minutes of slitless spectroscopy across 6 fields, and around 125 square arc minutes of deep JWST imaging in these fields. And you have complementary HST imaging and additional data there. Okay. So the 6 fields were really chosen to make sure we maximize number of intervening metal absorption line systems, their redshifts, as well as any Lyman alpha transmission spikes that might exist along the line of spike. We were very fortunate that the first object, J0100, at a redshift 6.3, very big, very bright quasar, was observed in August. We have been analyzing the data since then, and first set of papers are coming out. I think the third object is scheduled to be observed in a few days, so we're very excited about it, what is coming next. So what I'm going to talk about is primarily going to be about J0100 observations. Yes. Just as a highlight, this is the deep image that we got with JWST. This looks incredibly better than it looked on my laptop, so I'm actually amazed when I see it. Every time it blows my mind. You can see all the little details, all the little galaxies that are showing up everywhere. And what do we mean by when we do slitless spectroscopy? That means that image is not enough, right? Every single point there has a spectrum associated with it. There are advantages of it. We don't have any pre-selection. We get a spectrum of everything. There are disadvantages of it, that we get a spectrum of everything. There's a lot of confusion. So this is an example of what we're talking about. This is a simulation, but our goal is to basically pick up emission lines objects there. So how does it look? So this is a zoomed in stamp of galaxies. These 2 galaxies are redshift 6 galaxies, okay? They look red because they have a lot of strong emission lines there. These green galaxies are actually low redshift H-alpha emitters. So when you do the processing and get the a continuum, a science image, you'll see that there are bright continuum light from these bright sources in the foreground. These are redshift 1 galaxies. And you have a bunch of emission lines. And then you have to do some processing of getting rid of the emission lines there. And once you do it, you get the continuum there, and you get some beautiful emission line spectra that you see of these galaxies. If you know where the position of the galaxy is, you know exactly what is the wavelength solution. Conversely, if you find a triplet, you can also figure out where the host galaxy is. Okay, we do it both ways. I just want to point out, you can see there is color gradient there. This is absolutely real. So you can actually get spatially resolved spectroscopy of these objects. This is mind-blowing. This is unheard of, before JWST came about. I just want to emphasize it. And it was easy. And this is one of our not even the brightest object. This is one of our common objects. Okay, I want to emphasize that. So what do we get after we do all this? So in one field, we get, at first shot, 117 confirmed O3 emitting galaxies. Okay, this is just redshift 5 to 7. And if you look at the galaxies, they're color-coded by their O3 emission luminosities. You see that there's clustering of galaxies. Okay, so if you zoom in there, you'd find that there are 3 prominent galaxy clustering that we pick up at 3 distinct redshifts. Okay, at the quasar redshift itself, we find a very strong overdensity of around 24 galaxies with a velocity dispersion of around 200 kilometers per second. At around redshift 6.7, there is an additional overdensity of around 12 galaxies, if I remember correctly, with a velocity dispersion of around 100 kilometers per second. This is, I presume it's now, I would call it close to the second highest redshift protocluster that you see in the universe from our previous talks. This is incredible. Like this, again, blows my mind what you can do about it. Now, if you take these galaxy spectra and try to do a joint analysis, you see a very tight mass-metallicity relations when you stack the spectra as a function of stellar mass of the galaxies. Now, this, first of all, tells you that there is a lot of chemical enrichment that's going on even in the early universe. Number 2, this strategy of doing things taught us one thing, which is pretty useful for people who will do future proposals, which I want to emphasize that, number 1, these galaxies are pretty low mass, they are very low dust, and they have pretty strong ionizing radiation. That basically means that these things kind of conspire to make them very bright in O3 emission. So if you're trying to do an efficient galaxy search, looking for O3 emission line is the best way to go. That is not all. This is, again, an amazing, around 20-hour long exposure spectra of the quasar. I can talk about it for an hour. It's just incredible. But what I want you to focus on are these little transmission spikes that you see in the bluebird Lyman alpha forest, because the universe is very neutral there, so you basically a gun produce and trough, but then you have a little bit of emission spikes coming. And we wanted to see if there is cross-correlation with presence of these emission spikes with galaxies existing nearby. Okay, you can do it for Lyman alpha, you can do it for Lyman beta, so it's definitely confirmed it's not a noise spike. You see it, and you can try to do a cross-correlation analysis between them. Once you do it, you basically get, and on this plot, I'm showing you as a function of distance from the galaxy, a 3D distance from the galaxy. On this axis, I'm showing you mean transmission over the cosmic mean transmission. So at low redshift, when the universe is completely ionized, you can see as you go further out, the galaxy has a pretty large neutral gas reservoir. If you go out, the background is basically ionizing things. But at high redshift, you can see this amazing spike. It tells you that, at high redshift, when the universe is neutral, galaxies are actually ionizing a big bubble around them. I'll just take a couple more minutes. That's okay. So again, we present the first optical spectra of quasars at that redshift. Just by looking at the HPA emission line width, we can figure out that the black hole mass is around 10/10 solar mass. This is massive at redshift 6.3. We also see that there is no lensing effect here, and this is indeed a puzzle that you have such a big black hole at those redshifts. And the last thing I want to say before I stop, I promise, is this is my pet subject, so I'm very excited about it. These are 2 galaxies that are showing up at redshift, pedestrian redshift of 4.2, 4.5, etc. But these are spatially resolved galaxies where we have spectra for every little pixel here, basically. And we see that, there are associated metal absorption lines which are showing signs of a lot of tidal interaction. Indeed, when you look at these galaxies, you start picking up a lot of strong tidal interaction in a spatially resolved manner. And if you go to higher redshift, at redshift 6, even then we're starting to pick up galaxies, which is near the quasar zone of influence, where the quasar's radiation is actually ionizing away any low ionization gas, and you only see highly ionized gas around the quasar in this case. So with that, I'm going to stop. Sorry about that.
Can take one very quick question. Yes.
Slide
15?
Yeah.
Okay.
I wanted to ask about 4363 and whether you have individual detections or if that's from stack spectra.
We do have individual detection for some cases, but these analyses were standards.
Thank you.
Yes, speaker will be online. We're not quite ready yet. It's Adam Karnal, and we'll speak on the surprising abundance of quiescent galaxies at redshift between 3 and 5. So,
Sure.
Hello, can you hear me okay?
Yeah,
Yes.
we can see that.
Slides looking good?
Yep. Go ahead, Adam.
Great.
Hear you and see the
Thank you
slides.
very much. And thank you very much for having me. I'm really sorry that I couldn't be there in person today. But I'm going to talk about some early work that I've been doing with JWST, and I'm here representing the high redshift group in Edinburgh. And since I'm the only person giving a talk from this group, I thought that before I went into the sort of main event of the massive quiescent galaxy work that I've been doing, I'd just quickly go through some other papers that we've been publishing over the summer, actually, just when the first data came out. So the first image from JWST, of course, was this SMAXO 723 galaxy cluster. And I had an early paper out looking at these 5 high redshift galaxies that were identified and targeted for near-spec spectroscopy within this cluster. So we identified these, their redshifts, and then took the photometric data that was available to do SED fitting to measure their stellar masses and stellar ages, which turn out to be very young. These are low mass galaxies just at the end of the first billion years of cosmic history, that have formed apparently most of their stellar mass within the last sort of 10 million years or so. Following that, we published a paper led by Callum Don, who's a PhD student at Edinburgh, which has already been mentioned a couple of times today, looking at the UV luminosity function at these extremely high redshifts. And the conclusions of this seem to be in pretty good agreement with what other people are finding, which is that the UV luminosity function is smoothly declining out past redshift 10, and that it's at about the sort of top end of the range of predictions that people were previously making for what we would find out here. And of course, the most sort of exciting highlight, I think, from this paper was this galaxy candidate here that we have just above redshift 16, which I think was a real surprise to everybody. And this is actually going to be the target of a near-spec DDT program coming in the next couple of weeks or so, hopefully. So we should know very, very soon whether this really is a galaxy at this extremely early epoch in cosmic history. Following this, we then had a paper led by Fergus Cullen looking at the UV continuum slopes of this sample of redshift 8 to 17 galaxies, finding again, as I think has been already mentioned today by some others, that these are extremely blue galaxies, but not so blue that we think that they are dominated or have a significant population of POP3 stars, metal-free stars in them. So that's the kind of high redshift or highest redshift focus work that our group has been doing so far. But personally, I'm more interested in the future of these galaxies rather than their pasts to get to the point that we observe them at. So I want to know what happens to these first galaxies like Sears 93316. And the particular reason why I'm interested in that is that I want to find out how the most massive galaxies in the universe, in the local universe, something like M87 pictured here, actually formed and evolved. And there are various sort of reasons for imagining that this kind of time sequence that I've put up here might hold. In particular, M87 is, as well as being one of the most massive, one of the oldest galaxies in the universe, and this is something that we commonly find. So if you want to grow very massive and become very old, you need to start out quickly. So what we'd like to be able to do is to trace this evolution back across cosmic time from the local most massive galaxies to these very early seeds. And there's a factor of about 1,000 in stellar mass between these two galaxies. So really, the vast majority of the growth that's needed to produce something like M87 is in the future of something like our Redshift 16 candidate. So part of that evolution might look a little bit like this. This is a spectroscopic survey with the ESO VLT called Vandals that was recently completed that I'm involved in, and part of that survey is targeting a sample of about 250 massive quiescent galaxies at about redshift 1 to 2-ish. And this is actually the oldest galaxy in the Vandal sample. It's very, very massive, has this very red continuum. And when we fit spectral models to this galaxy, what we find is that it appears to have formed the vast majority of its mass at least 5 billion years ago, back within the first sort of billion years of cosmic history. So I put up here, and hopefully you can see it, the formation redshift that I measure for this galaxy is about redshift 7, and what that means is that's the time at which half of the mass that's currently in the galaxy had assembled. So what I'm saying here, or what this seems to be telling us, this spectrum, is that this galaxy had already reached a stellar mass of about 10 to the 11 solar masses, comfortably within the first billion years of cosmic history. So this tallies with the extreme age of galaxies like M87, but it poses a challenge as well, because we don't really think that we can see massive galaxies, or previously to JWST at least, massive galaxies at these extreme redshifts. And it's certainly not something that's historically been predicted by simulations of galaxy formation. So it becomes very difficult to actually go and try and find these things when you get out past about redshift 1 to 2-ish, out to redshift 3 and 4 or so. And I think this galaxy here is a really nice example of why that's the case. So this is a galaxy from the Candle's EGS Catalog, and it is clearly detected in several bands. We know it's there, but that's about all that we know about it. You can see up here from a spectral fit that I've done, this galaxy has a posterior median redshift from these data about redshift 3, but the uncertainties are absolutely enormous. In fact, this galaxy could be almost anywhere at any point in cosmic history from about redshift 1 to redshift 8 or so. So, you know, you'll all be aware who've worked on these kind of candles data that the catalogs are full of these kind of galaxies. They're out there, we know that they exist, we have several detections of them in different bands, but more than that, it's very difficult to actually say. And the main reason for this, of course, is that the limit of Hubble Space Telescope's wavelength range is where I put this black line just here. And beyond this, further into the red, into the infrared, we're relying on a combination of ground-based data in the K-band and Spitzer Iraq data at longer wavelengths still. And this is obviously data that's come out of a phenomenal progression of engineering and scientific and technical challenges, but it's just really struggling to give us the constraints that we need to characterize in detail these kinds of galaxies, these red faint blobs that we see. So these kinds of comparisons have already been put up a fair bit so far, and I'll make it again. This is some of the best available Spitzer Iraq data, and this on the right is a prediction for the JWST Primer survey, which is led from Edinburgh, and the improvement here is just unbelievable. This isn't actually real data yet. We're still kind of waiting for Primer to execute, hopefully the first tranche of data coming later this month. But I think this is a really good illustration of just the incredible improvement in the data that we're getting out past sort of 2-3 microns from JWST. So, of course, in the EGS field, we now have Sears, the first epoch of the Sears data. And my choice of object earlier was no coincidence, because, of course, this galaxy is one that's within that area of these first 4 Sears pointings. And when we add on the JWST data, we go from this very poorly constrained redshift 3-ish solution to this extremely well constrained redshift 4.3 solution, with these multiple extremely high signal to noise detections in all these different bands that really pin down what turns out to be a very, very large Barber Break in this galaxy. So not only do we have a very good constraint now on the redshift of this galaxy, we're also pretty confident that it's already shut down its star formation only about 1.5 billion years after the Big Bang. And in much the same way as Guido was talking about earlier, we were maybe expecting 0 or perhaps one of these things, but actually in this even very small 30 to 40 sort of square arc minute Sears area, we found 2 of these massive quiescent galaxies above redshift 4, which is a real surprise, and I'll get into that a little bit more in a minute. But I first wanted to just mention something really exciting about this galaxy, which is that it's kind of hiding out behind this fantastic barred spiral galaxy just here, which is kind of in the way of this very faint compact red thing that we want to look at. And this is the point where if I was in the room, I'd probably solicit suggestions as to what you think the redshift of this beautiful, fantastic, resolved, grand design type spiral galaxy is. Seeing as I'm not, I'll just tell you actually, regardless of the fact that it kind of looks like a very local, fantastic, beautiful galaxy, it's actually already at redshift 2. So this thing is most of the way over on the other side of the universe, but still with JWST, it's too bright and too shiny, and it's in the way of the faint red thing that I desperately want to learn about. And the cool thing about that is that at HST sort of wavelengths down here, and also you can imagine at lower spatial resolution, this thing just looks like another part of the extended structure of this spiral galaxy. In fact, it wasn't even identified in the Candles catalog. And it's only at sort of 2, 3, 4 microns out into the red that you really see this thing pop out as its kind of own independent compact source, which is about redshift 4.2 or so. So 2 very robust candidates at redshift 4 to 5, and actually significantly more than that at redshift 3 to 4. At both of these sort of redshift bins, we're finding an awful lot more quiescent galaxies than we previously would have expected to find, or indeed other studies of this field using just the HST candles data were able to identify. And I've just kind of quantified that on this plot that shows you the number density of massive galaxies above 10 to the 10.5 as a function of redshift. So this grey line here from Derek McLeod's mass function paper in 2021 is for the whole galaxy population, and this red line is for quiescent galaxies. And these studies in green and blue here, just a very small sample of potential. Oh, hopefully I've just seen the camera move around. Hopefully I'm still there. These are studies that focused on redshift 2, 3, 4, 5 massive quiescent galaxies, and all in reasonably good agreement. But what we're finding in this new JWST data is much higher number densities than that. And I think the reason I moved this plot over to the left here was because I was intending to put some possible explanations for this up on the right, but apparently I didn't do that, so I'll just take you through them. So of course, one thing that could be going on here is that we're surveying a very small area of sky. It's only about 30 to 40 square arc minutes, as I was saying, and maybe we just got lucky. Maybe this is a very overdense area. We know that quiescent galaxies and massive galaxies at lower redshift are very strongly clustered. So perhaps this is a very unrepresentative bit of universe at this redshift. And as we've already been hearing about earlier today, several other large surveys at much larger areas are going to be conducted in the coming months. And I think that this is a question that we will answer very, very quickly. And another, though, possibly more intriguing possibility has to do with the way that we model these galaxies and fit their star formation rates and star formation histories. And this is a very quick demonstration that I wanted to show of some star formation history prior analysis that we did in this 2019 paper, which shows that actually the typical sort of exponentially declining star formation history models that people typically use are actually quite strongly biased towards returning you star-forming galaxies. And that means that if you have relatively poor constraints, you're more likely to come down on the side of star-forming rather than quiescent. It's only when you get much better data, as we recently have, that things get pushed away from this kind of prior preference for star forming towards quiescent. So again, I think we're just going to have to wait for larger areas to be able to know quite what's going on here, but it's intriguing nonetheless. And the last thing that I just very quickly wanted to mention is my own PiJDSD spectroscopic program. This paper that I've just published is not the first one that I had selecting these kinds of galaxies, and in fact I published a paper in 2020 using the best available CANDLES data from Good South and UDS, which turned up this candidate, which looks like it's a passive galaxy at about redshift 4.7, and we applied successfully in cycle 1 for spectroscopy to cover this with the R of 1000 gratings in these two wavelength regions. And this is the predicted data that comes out of this model in the JWST ETC. And I've been showing this plot for quite a few years now with this question mark at the end of the title. And thankfully, finally, just last month, we got the answer to this question because the data were taken. And I can confirm that this is now known to be a massive quiescent galaxy at redshift 4.7, which is by some reasonable margin the highest redshift quiescent galaxy that's ever been spectroscopically confirmed. And this is an incredibly rich data set, which I don't really have the time to go into in a lot of detail right now. The analysis is still ongoing, but it's something that I hope to be able to share in a paper that's coming up very soon. So that's everything, and thank you very much for listening. Happy to take any questions.
Okay, thank you, Adam. There's time for a quick question because everybody's using all their time. Yes, Richard.
Oh, beautiful data. So you didn't say anything about the ages of these objects beyond a redshift of 4. So, you know, you started by talking about the assembly history of the earlier objects, but these objects beyond a redshift of 4, when did they form most of their mass?
Yes, I mean, as you know, it's very difficult to say that from just the photometric data. And we did make a preliminary attempt to do that, and it looks like they're forming somewhere between redshift 6 and 10 most of their stellar mass, which is consistent with work by people like Ivo Labe. But really, you need spectroscopic data like we've just had to come through for this redshift 4.7 object to answer that question in detail. So that's going to be the main thing that I aim to do with that.
Thank you again, Adam. So our next speaker this afternoon is Jehan Katra-Telpe, who is going to speak about the growth of galaxy structure in the early JWST imaging era.
All right, thank you all. It's wonderful to be here. I have to say it's a great honor to be here to present some of our early work with JWST data, and it's also a great honor to be among some of the first users of this amazing facility. So like everyone else, I'd like to thank. Move it up. It's not on. Green is on. All right, now I'm louder. Sorry about that. So I was saying that I think it's a great honor to be among one of the first users of this telescope, and I'm excited to get to tell you about some of our early work looking at the structures of galaxies. Like many of you, I was excitedly awaiting for those first images to be released in July. We've seen lots of examples of beautiful images today, beautiful mosaics. And like many of you, the days after these images were released, I was zooming into things, looking at all these galaxies, because we could see all of this amazing structure at galaxies, nearby galaxies, and what used to be high redshift, which isn't anymore, because, you know, things have changed. And so I'm going to tell you a little bit about some of the work we've done looking at these morphologies of galaxies in the Sears field. So it has been nearly 100 years since Edwin Hubble first put together the picture of the Hubble tuning fork diagram that we're all familiar with. Right? For most of our lives, we've learned that galaxies in the nearby universe are typically either disks or they're elliptical galaxies. And Hubble, the telescope, has helped us to push this understanding out to cosmic noon, where it was able to obtain rest frame optical imaging out to about a redshift of 3, especially thanks to the WST3 instrument on Hubble. And so we now know that the basic underpinnings of the Hubble sequence were already in place at these high redshifts. You know, at 4 billion years ago, 11 billion years ago. We see at these redshifts galaxies that have disks, galaxies that have spheroids already. And so we'd like to understand what galaxies were like at even earlier times, right? In short, when did the very beginnings of the Hubble sequence come into place? When did structures like spiral arms, like bulges in galaxies, when were they first able to form? And what were the physical processes responsible for their development? And so for this project that I'm going to talk about, we looked at galaxies selected in the June footprint of the Sears survey. So Steve Finkelstein already gave a great overview of Sears, so I don't need to introduce it. But we looked at 850 galaxies in that footprint that were detected with Hubble, so that we could directly compare morphologies from the Hubble imaging with morphologies from JWST. And these are all galaxies at a redshift greater than 3, where Hubble was no longer able to probe the rest frame optical, but instead was sensitive to the rest frame UV. So shown here is the redshift distribution, and you can see most of those sources lie between about a redshift 3 to 5, and then there's a tail out to higher redshifts. And so we had our team conduct visual classifications of all 850 of these galaxies. So each galaxy was looked at by at least 3 people. And we used this classification scheme where people had to decide, well, do you see the presence of a disk? Do you see a spheroid? Is the galaxy irregular? Is it a point source or unresolvable, or is it junk? Can you not see anything about their morphology? And because of the complexity of galaxy morphologies, we intentionally made this not mutually exclusive, because some galaxies can have a disk, but still have a bright, spheroidal component if there's a bulge in the center. So the example shown here on the left is one of those objects. So the classifiers had to look at all of the postage stamps for all different bands like this, and with the Hubble imaging below. So because these classes are not mutually exclusive, there end up being 7 possible combinations of classifications in the end, right? There's systems that only have a disk. There are systems that have a disk and a prominent spheroid. There can be things that are a disk but have irregular features, and so on. So this gets to be fairly complicated really quickly when you consider all these different combinations. So the next couple of plots I'm going to show you have all 7 of these combinations plotted, so there's a lot of information. All right, so what's shown here are the results from Hubble, which we will compare to JWST in a moment. And so this is a compilation of classifications from candles for all of the candles fields using Hubble data. And they're broken down into those 7 different classification groups I mentioned in different color codings. So things to pay attention to. Here's all the things that have disks. So from Hubble, we saw redshift 3, around 40% of things had disks, and then they fall off. Galaxies with spheroids, something like 30% of things had a spheroid, and that falls off at higher redshift. Likewise, irregular galaxies fall off. And this fall off is really driven by this last panel, things that are unclassifiable or have a point source, because it's really hard at these very high redshifts to be able to say much about their morphologies. If we then look at the 850 galaxies we classified from JWST, this is what we see. Basically, everything goes up, right? We have a higher fraction of everything across the board. And you can kind of go back and forth, right, and see that the fraction of things with disks is much higher. 60% at the lower redshift end starts to fall off. Fraction of things with spheroids is 40%. Fraction of things that have irregular, kind of 40% across the board at all redshifts. And almost none are now in this unclassifiable state. So you might be curious about, okay, well, are these the same objects? Are you comparing apples to apples? Well, no. So here are the exact same objects being compared for just some of these groupings. So because these were only the things in the June footprint of the EGS field with Sears, there's a smaller number of them that we had candles classifications for. And so what I want to draw your attention to is just the difference. The color points here show, again, the JWST classifications. The stars show what we would get from just the Hubble imaging. And the big difference you see is a component of things that we now can see a disk in, you would have said was only a spheroid if you only had the Hubble data. So what are some of the reasons that these fractions seem to change as you go from the Hubble imaging to the JWST imaging? Well, of course, the wavelength that we're observing at makes a difference, right? We're now able to look at rest frame optical morphologies all the way out to these really high redshifts, which we couldn't do before. So Hubble was sensitive to the rest frame UV, and you're seeing some different structures. There's also a difference in the resolution of the images, so we can see more detailed structures than we could with Hubble. And then I think the one that makes a really big impact here is the depth. With the Hubble imaging, we weren't able to see a lot of the faint, low surface brightness features that we're now able to pick up with JWST really quickly. And so a classic example of this are things that we see that have disks now with JWST that if we only looked at the Hubble imaging, we would have said it was a spheroid. And so here's some example objects where people found very different morphologies as you looked at either the Hubble imaging or the JWST imaging. The left column shows the HST F160 image, and then we have 3 different filters with JWST, and then the color combined image here on the right. And, for example, this object right here, the second one, with just the Hubble imaging, it looks really, really small and compact. And so if you were forced to classify this, you'd say, okay, well, that's compact or it's a spheroid. But once you have the JWST imaging, you can see the fainter low surface brightness features around that and see the presence of a disk. In addition to the visual classifications, we conducted a number of different analyses of different quantitative measures of morphology. I don't have time to talk about all of them, so I'll quickly just show you what the Sursic indices for these sources look like. These are color-coded by the different combinations of classifications in the same way as the other plots were. So we have things with disks on the top, things with spheroids in the middle, and irregular things on the bottom. And so we see overall that there's a broad distribution of Sursic indices. Galaxies that have a disk peak near n equals 1 with a tail out to higher n. Galaxies that have a spheroid probe a really broad range. And irregular galaxies peak at n less than 1. And so, what's commonly done in the literature is, people make a cut, to value of 2 or 2.5 or something like that, and say everything below this is a disk and everything above that is a spheroid. But we already know from Hubble imaging that that's not completely correct. You have a lot of overlap of these populations. And we're seeing the same thing with the JWST images. Okay. So finally, this is really just the tip of the iceberg, right? Somebody said this morning, this is really only 5 months of data, and it's hard to believe, how much we've done as a field in 5 months. And cycle 1's not even done, right? There's a lot of data that's yet to come. I talked about 850 objects. By the end of cycle 1, we're going to have many, many thousands, at these high redshifts. And so we're going to be able to study things in a statistical sense that we haven't been able to do before. And so this diagram from Brent Robertson's paper really nicely illustrates the collection of these extragalactic deep fields that will be taken in cycle 1. And that includes things that go really, really deep, like NG Deep, and things that go really wide, like Cosmos Web, and then everything in between. And so by the end of cycle 1, we're going to have a very different picture, I think, than we even do today. And so I'm really looking forward to seeing that. All right, so to summarize, we see that there's a wide diversity of morphologies in galaxies all the way out to at least redshift of 6 and likely beyond. We see a large fraction of galaxies with disks that seems to drop a little bit at the higher redshifts. We see a large fraction of galaxies that have irregular features, about 40 to 50% across the entire redshift range, and we see spheroids across the entire redshift range at a lower level. But keep in mind, these fractions aren't absolute because there are observational effects that are in play. So things like low surface brightness features and disks can be really hard to see at the higher redshifts, and so that's something to take into account. Further work really needs to be done to quantify the properties of these disks. We see these disks out to the highest redshifts we've been able to see so far. What are they like? How are these disks different from the disks in today's universe? And so more work is needed to answer this question. And with that, I'll end here, and I'm happy to answer any questions.
Yeah, I have a question from online. So Candace found redshift 1, 2, 3 galaxies with stellar mass below 10 to the 9.5 were prolate, not disks or spheroids. How many prolate galaxies are you finding in Sears?
How many prolate galaxies are we finding? That's a good question. I don't have the plots up here that would show that. I think that's still TBD whether things are actually prolate at these redshifts. So.
Quick additional question from online. Yeah. Have you also documented mergers?
I'm sorry, could you repeat that?
Have you also documented mergers?
Have we also documented mergers? Yes, we have. And work will be forthcoming very soon on those. But that was part of the classification, was to identify mergers.
Great results, Jan. I was wondering if you can comment on whether or not it's a problem to have so many disks so early and so stable over all this time.
Yeah, is it a problem that there's so many disks so early and the fraction seems to be relatively stable? I would say the jury's still out on that. You know, through some of the initial comparisons we've done with simulations, it doesn't seem to be a problem. The simulations have as many, if not more disks. The question of how stable they are, I think we don't really know that. So further work needs to be done on that.
Thank you very much again, Jehan.
Thank you.
There you are. Next speaker will be who will tell us about the chemical evolution of redshift greater than 7 with
Okay. Hear me? Hola? Okay. Let's see. Okay, thank you. So thank you very much. I'm very excited to be here presenting this talk. I'm Carla Lellano Cordova. I am a postdoc at the University of Texas at Austin. I work in the research group of Daniel Berg. So I will present these results that we get for the abundance patterns of different abundance in addition to metallicity. So this is my collaboration group. So in this picture, you can see different objects that can be noted at different redshift. So the emission spectra of these objects can give us information about the physical conditions like electron temperature, density, the chemical composition of the interstellar medium. So the metallicity is a key parameter that can give us information about the essential processes involving galaxy formation evolution. As you know, the metallicity is correlated with the stellar mass. So as you can see here, this mass-metallicity relationship. So in this relationship is involved of different evolutionary processes, like the building up of metals by star formation, the outflows that remove these metals, also the inflows of pristine gas that activate also the star formation, and also are ejected to interstellar medium. So, but also the metallicity is very important key to share the mass-metallicity relationship. It just depends on how it's calculated, for example, with a direct methods or with different strong line methods. So in this work, we analyze these 3-length galaxies observed for JWST, of course, and with these galaxy clusters, these spectra come from the early release observations. We use the post-processing spectra of NIRSpec that were presented in Trump 22, and also the data analysis of this spectra is in Arrabal Arrow in preparation. So as you can see here, the redshift of these galaxies, we also calculate were confirmed also with the previous works in the literature. So the objectives of this work is to evaluate the quality of this spectra, explore the determination of the nebular properties, give a first look to the mass-metallicity relationship, and also to the neon and carbon abundances of these hard redshift galaxies. So to do that, we analyze individually the two different visits that we have for this spectra. Here you can see the red frame spectra from the UV and the optical from the high redshift galaxy for this sample. You can see here also the two different samples. So you can see all these emission lines. I want to highlight a 4363 that is very exciting to have this line at this redshift because it will allow us to determine in an accurate way the metallicity. So we determine the reddening using the Balmer lines and also, well, the electron temperature. So, but we will look very close to 4363. As you can see here in these three plots are the three galaxies in the range where is 4363 line. So first we compare these two spectra for the two post-processing spectra for the two different visits and also with the original ones. So first you can see that there is differences in between the two visits, but the most interesting thing here is that we can see this kind of structure in the 4363 lines. We don't take into account this profile, we can underestimate our electron temperature. So, but interesting is that in that position of this profile, we can see this we can see here the emission of iron 2 4360. This means that this profile is exactly in the wavelength of this line. So, however, this iron 2 lines is detectable in high metallicity galaxies, as you can see here in this example. So, but there is also could be a possibility about this odd behavior of 4363 that this could be an artifact due to a different other sources that we also listen to in the morning. So, but to calculate the electron temperature in this analysis, we take in consideration all these sources of uncertainties. So here is the electron temperature for these three lens galaxies. For the higher redshift galaxy, we couldn't determine the electron temperature, even we can detect the line. So we use electron temperature that is typically for star-forming galaxies. So here is the metallicity that we calculated, comparing the two different visits, 007 and 00A. And you can see here, at least for these two galaxies, that the metallicity is slightly higher in comparison with 007. As you can see here. So also we determine the ionization parameter using the oxygen 3 and oxygen 2 lines. And we got that the ionization parameter in average is very similar to nearby extreme emission lines galaxies that are reported and also in other worlds. For this galaxy, we also have a very high ionization parameter for the two different visits. Now that we have determination of the metallicity, we also analyze or give a first look at the evolution of the mass metallicity relationship to higher redshifts. As you can see here, this is our result. We also add another studies from the literature previously to the I am presenting here, but also we add these star-forming galaxies in the local universe that is reported for BERT 2022 for the Class C Treasury survey. And you can see here that for these two galaxies, this previous determination of metallicity also use the direct method, but using a different approach. But we can see we have a consistent result in comparison with our result. However, for this higher redshift galaxy, the higher of this sample, you can see two different results. This gives us two scenarios. First one is that if we take the higher result for the metallicity, we can see that the slope of the high metallicity relationship is similar to the local star-forming galaxies. This implies a little redshift evolution. However, if we took the lower metallicity for this galaxy, we can see a steeper slope, and also the trend is different to the local star-forming galaxies. It could imply a stronger influx of pristine gas or weaker outflow of rich gas of high redshift galaxies. However, you can also see that the dispersion that we had for local star-forming galaxies also is high, and these galaxies also are consistent with a little redshift evolution. So for a clear interpretation of the mass metallicity relation, a higher redshift, we also require a larger samples of galaxy with high signal to noise and robust absolute flux calibration. So, but continue now with the abundance patterns. The nearest spec from these three galaxies also allows you to calculate the neon abundances. So neon is produced for massive stars, so it's expected that this neon overall is constant with metallicity, since oxygen is also produced for massive stars. So that we calculate for these three galaxies using the neon 3839, and this is our result. Here is the neon overall versus metallicity. This is our results. So this is a comparison also with X2 regions for several spiral galaxies and also dwarf star-forming galaxies. And you can see that for neon, we don't find any evidence of forced cosmic evolution. And also, these values are in agreement with what we find for dwarf star-forming galaxies and also for the solar abundance. So, but here now we look to the UV in the reference UV, and you can see also the different lines. But also, that I want to highlight is the detection of carbon-4. So it is very exciting because we can study with JWST observation the evolution of carbon at very high redshifts. So carbon is produced for intermediate mass and massive stars. In this expected, you can see this kind of trend. So our result for this carbon is this. So we calculate carbon-3. So here you can see all the different objects. We have X2 regions for high metallicity, determined with different emissions lines, and also we have here the dwarf star-forming galaxies with redshift 2, and this is our result. So first, we find the carbon over oxygen for this high redshift galaxy is consistent with observations. However, you can see that this carbon overall is highly uncertain, that I can see. So also we have here the dispersion of this in the local universe that is also high, which means that we need robust measurement also for these carbon abundances to determine what drives chemical evolution of carbon. So finally, well, this is my summary. I think the most exciting thing here is that we can determine direct abundance metallicities at higher redshifts. This implies that we can have more robust determination or robust explanation about the different processes driving mass metallicity relationship. We have, with this analysis, we have two different scenarios, and also for the carbon and neon abundances, we give the first reference of the values, or the expected values for the high redshift galaxies. At least for this study, we don't find any evidence for cosmic evolution. Well, thank you.
Thank you for this really nice talk. I was wondering, it seems the flux calibration for near spec is limiting you. Sort of what level do you need before you feel like you can make definitive statements? Like what precision or accuracy in the flux calibration do you need?
Well, I think it's a good question. I don't know, more or less. So one of the things here in this work is that we are analyzing the relative flux calibration, the relative fluxes of these lines, and it can permit to guide this exploration. But exactly, no, I don't know.
Hi, this is a great talk. I'm Alec Hirschauer here from ST. I'm trying to wrap my head around this mass metallicity relation that you've presented.
Yes.
I guess first question, sure, you can leave it on the results slide, actually.
It was there.
So on the results slide, you have the two different possibilities are the very little evolution with redshift, and then secondly, stronger infall. And I guess my first question is, are those mutually exclusive?
No. It's like an only explanation with the analysis of this. Yeah, but they can exist also more, because you can see here that at least for these two galaxies we had a more or less consistent result, but you see this very cut here on the results, and in this conclusion for the scenario depends on the metallicity of this. And for one of the visits that we calculate here, for example, we couldn't determine the 4363 temperature. That is important for this analysis.
For sure. And I guess follow-up is that my recollection on work done with evolution of mass metallicity as a function of redshift is typically with higher mass galaxies just out of necessity, right? And how is that inconsistent with that first possible result then?
And the another thing is that this is for all these galaxies direct method. So the another is the strong line method that you can see how it changed the differences for the methods. So yeah.
Okay. Thanks.
Thank you very much again.
Thank you.
Thank you. And our next speaker is Massimo Pascale. Okay, you're okay. Who's you'll talk about unscrambling a lens arc in a SMACS cluster.
Yep. Okay. Okay, cool. Okay, can everybody hear me okay? Fantastic. Okay, then I'm going to get right into it. So hello everybody, I'm Massimo Pascale. I'm a graduate student at UC Berkeley. Before I get into the talk, I just want to say that I really appreciate you all for being here, and I'm very thankful to be here. This is my first conference since the advent of the pandemic, and I'm really excited to be back. So today I'll be talking about unscrambling the lens galaxies in SMACS 0723, which is a project on the first publicly available JWST data that was released. I don't know if you all remember back in July, but it was actually a White House press conference of all things where they showed off this image. And it was a pretty stressful day. It got delayed, I think, by 90 minutes. And then finally, when we got to see it, we barely even got to see the image. It was off in the background as the president was presenting the whole thing. And my colleagues and I are very interested in galaxy clusters, and specifically the lensed galaxies that we see in front of these clusters. And so during that whole press conference, we were trying to take screenshots, low-resolution screenshots, trying to pick out all of these lens galaxies that were literally popping off the image, right? Even in that low-resolution screenshot, you could see it. And then right after the press conference, the full high-resolution image was uploaded to Twitter, which apparently a lot of astronomy is done on Twitter now. And we were actually able to start going through and what we call unscrambling these lens galaxies. And by that, I mean that we were trying to pick out the multiply imaged lens galaxies that we could see in the cluster. Multiply imaged meaning that there's sets of lens galaxies that actually all correspond to the same background object. These are very important because they provide powerful constraints for modeling the cluster mass distribution, which is acting as the lens. It's something called strong lens modeling. And so before I get specifically into the project, I do want to give a little bit of a brief overview of the cluster itself. There we go. I think now the cluster has generated a lot of buzz and a lot of hype, and it's very well known by a lot of people. But prior to the release of the JWST images, I think it wasn't very well known, despite it having actually a lot of existing data. There are 7 filters of HST, thanks to it being both a SMACS as well as a RELX cluster. Additionally, there's also Muse IFU spectroscopy that could be used to get spexies of the giant arcs that you can see in the cluster. And so another group had taken this existing data and actually done what we did for the JWST data, which is to identify these sets of multiply imaged galaxies. They were able to find 5 sets in the HST data, and then used the Muse data to identify spectroscopic redshifts for 3 of those sets. So altogether, they were able to use that lensing evidence to reconstruct the mass map of that cluster lens. And so what you're seeing Over here is the resulting, what they call the critical curve. That's a product of that lens model. And this is just the locus of points for which if images appear about them, they diverge towards infinite magnification. And they found that the mass was about 10 to the 13 solar masses, so kind of on the cusp between cluster and galaxy group. So now enter the JWST era. We get 6 filters of JWST NearCam, and we actually got a lot of exposure time for it. This wasn't just any random image. We got extremely good data handed to us on a silver platter. Additionally, we also got NearSpec as well as MIRI and NearISS. But I kind of want to just get into the comparison between these two images, which I think this is the 3rd or 4th time it's been shown today, but man, I never get tired of this. I don't know what could be a better comparison to show the raw, awesome collecting power of JWST. And so, as I mentioned earlier, you can literally see all of these giant arcs really popping out compared to the HST color image. And so let's look at a few of the ones that have been previously identified kind of in greater detail. And Dan had pointed this out earlier, but we see these kind of compact knots about these lensed images that we didn't see at all before. And so I too had also postulated that maybe we were seeing some sort of very young object, but further work has actually shown that there are evolved globular clusters that we're able to see now in these JWST images sort of off the midplane of these lens galaxies that we couldn't see before. So what my colleagues and I wanted to do was to comb through this JWST color image and pick out as many sets of multiply image lens galaxies as we possibly could, each one providing more and more constraints on the cluster mass distribution for strong lens modeling. So we picked them out mostly based off of similar colors and morphology, intuition about where they should appear because the lens had already been previously modeled with HST data, and then we're able to actually vet them through the strong lens modeling process to further confirm them. And so overall, we identified 14 new sets of these multiply image galaxies. This is like a factor of 4 overall improvement. We go from 5 all the way now to 19. So we're able to constrain the cluster mass distribution much greater. Individually, this amounts to 42 new individual images. You're seeing right here is all of those images labeled. I know it looks very crowded, but there's just so many that it's difficult to pack it all in. A funny story, I think there was some popular YouTube science person that thought that these were spectroscopic redshifts and not individual labels. I wish we had found a redshift 19 object. So taking all of this new lensing evidence that we have available to us because of JWST, we sought to model the cluster mass distribution. We did this through a parametric lens modeling method, and by that I mean that any individual mass component was a fully analytic, fully parametrized component. And if you're familiar with Lens Tool, it's very similar to that. And so taking this modeling method, we reproduce the data that we input, which is the multiple image positions, to less than half an arc second. So this is an extremely good fit. The model is a very good fit to the input data. How does it compare to the HST-based model? It's in general agreement, which we would expect, right? We're still using the same multiple images that went into that HST-based model, so we don't expect massive differences. But the mass did go up a bit, and something that I'm interested in is that the sort of overall shape of the critical curve, which I have plotted there, has sort of become more elongated. It's a lot more peanut-shaped, I think, compared to the previous HST model. And so this might mean that the entire mass distribution itself is sort of more elongated, which is, usually characteristic of clusters that might not be fully virialized. So to further explore this, I took contours of constant surface mass density, which we get from the lens model. I plotted it on top of this extremely stretched out version of the SMACS 0723 image. That way we could compare the intracluster light to the mass distribution that we had gotten from the lens model. And so you can see that they both sort of follow this same elongated shape, very similar profile, potentially cluing into maybe the ICL tracing the dark matter in this case. And if you look even closer, you can see a lot of substructure in the ICL that was not visible before. In fact, if you go through, it's a lot of those redder bands that we get just from JWST that allowed us to see this structure. There's this sort of lobe feature up here, or this lobe feature down here, as well as this loop up here. And as far as I know, seeing this level of substructure within the ICL was unprecedented up to this time. And so this further clues me into the idea that maybe we're observing some sort of dynamical disturbance in action, and maybe we're seeing the buildup of this cluster going on right in front of our eyes. So I've talked a lot about the cluster itself and the mass distribution. Now I want to kind of turn to those beautiful lens galaxies that I had pointed out earlier. In particular, I want to talk about this image ARC5, Arc 5 is what we call a caustic crossing arc. That means that its lensed image appears about the critical curve, which I've plotted there in the dashed line. And actually, it appears reflected across it. So all features that you see on one side, you should be able to see on the other side in the exact reverse order. And this is predicted by strong lensing theory. Every component that you see on one side, if it's strongly lensed, should appear on the other side. So then I want to focus on these two blue knots here that should correspond to the same background object. They're just reflected across the critical curve. And since they're very close to that critical curve, which is where I mentioned the magnification diverges, and they're very compact, the lens model predicts that the magnifications for these should be extremely high, factors of hundreds for these objects. This could be implying parsecs or tens of parsec scales for these individual objects that might be star clusters within that lensed galaxy. And now I want to point out one other object that's right next to what I've labeled as A, which I call TR, which is this red object right here. I know it's a little bit hard to see. But you'll notice that there's no other red object next to B. It's only next to A. But I told you that because of strong lensing and because it's reflected, we should see it, right? That means that there might be other lensing at play, specifically microlensing. Perhaps there's some compact object within the cluster that's passing in front, compounding that lens and getting even greater magnifications than we had before, potentially factors of thousands. And so this offset red knot could be an extremely magnified micro-lensed object. And I think it's sort of difficult to see in the color image, but it becomes more clear when you go to see all of the different JWST near-cam filters. So first, those B and A, those two compact blue knots that I pointed out earlier, those are very visible in the bluer bands. But then as we go to the redder bands, they slowly fade out, and that red object TR fades in. By the time you get to F44W, TR is the only object that you can see. Now the PSF is a lot worse in this band, so it's a bit difficult to make out. So I've subtracted off that underlying arc background so you can see just the knots in the insets here. And so I think this is the most convincing bit, is that if you look at the F200W inset, you can see the two blue knots, and probably TR is also there on top. And I've marked the position of B with that red cross. When we go to F444, that red cross no longer has an object underneath it, and all you're seeing is TR. So potentially we're seeing maybe an individual cool red supergiant that has been micro-lensed to extremely high magnifications here. Further spectroscopy and SED fitting could probably prove this. So now I just want to give some conclusions and then a little bit about future work or questions that we had at the end of this work. But apparently everybody works very fast in 5 months, and so most of those questions that I'm putting down here have actually already been answered. So JWST has afforded massive improvements in finding strong lensing evidence and doing cluster lens modeling. I think if you're at all interested in galaxy clusters, the buildup of galaxy clusters or high redshift galaxies, you should really be excited about what we're doing here. And a number of other people have already given very exciting talks about that. We're also seeing previously unseen substructure in the ICL, potentially cluing into giving us the history of the buildup of these galaxy clusters. And another work has already gone through specifically with this cluster and modeled that ICL and found some very interesting conclusions about the potential disturbance that could be going on in that cluster. We're also seeing giant arcs in incredible detail that we've never seen before. I mentioned in one of those other, earlier, in one of those arcs, we had seen compact knots that were evolved globular clusters. But potentially, we could even be seeing the progenitors of globular clusters in other lensed images in other galaxy clusters. You should be definitely on the lookout for that. And finally, caustic crossing arcs like Arc 5 open up the door for caustic transient detection. We could be seeing extremely magnified stars at cosmological distances, thanks to JWST. Thank you all so much for your time.
A question from online. So, would it make sense to rebook at 10 years intervals to see dynamics?
Sorry, can you repeat that?
Yeah. Would it make sense to rebook, re-look at 10 years intervals to see dynamics?
To look at it again in 10 years? Yeah. I don't think we're going to catch anything on that time.
Very nice talk. What is the uncertainty in the magnification factor along the critical line? If I want to measure the size of an object, how uncertain is it?
Right, yeah. So the magnification uncertainty can be pretty large, especially in that regime right next to the critical curve, where the magnification very rapidly approaches very large magnifications. So I had mentioned those two blue knots, A and B, and I'd said it was factors of 100. To give you an idea, the uncertainty is about the same order of magnitude. So it's, 100, or it's like, 500 plus or minus 300 or something like that.
Hi, Jesús Vega Ferrero from the Instituto de Astrofísica de Canarias. I wonder, I have a double question. So usually radial arcs are masked by the VCG because they are close to the cluster center. So I wonder if JWST will have to unveil more radial arcs. And the second question is, did you find any radial arc in this cluster?
You're talking about subtracting off the bright cluster light to determine more arcs?
Mainly radial arcs that are closest to the cluster center.
Yeah, yeah.
Not tangential. Many of the arcs that we saw in the image are tangential arcs.
Yeah, I agree. Yeah, definitely one of the next steps here would be to do very precise modeling, not just of the ICL, which also kind of contaminates our ability to see all of these arcs, but also those bright cluster galaxies to determine more of them. We haven't done that in this specific cluster. I know there have been follow-up works that have subtracted off some of the bright cluster galaxies. I don't think they were particularly interested in the lens images when they did that, but there could be some collaboration there that I think could result in something nice.
Very nice work. I want to know that for lens modeling, you sort of need the redshift of the galaxies. So are you using just photosys from HST when you produce those mass model? And another thing is, I know this field has nearest Slitless Spectroscopy data. So for some of the sources, you have SPECT and lens model will be much better. Do you know if any lens modelers are looking at this?
Yeah, so the lens model was constrained based off of those 3 spectroscopic redshifts from Muse that I had already mentioned. We had tried to get more with the existing near spec pointings. Another group was actually able to get 1 more spec-C, but most of them either weren't on any of the arcs or didn't really result in anything. I don't know if anything has come up from nearest, but of course there is nearest data. And we would expect that to improve things. There are multiple other groups that have done lens modeling on this cluster, and all of our models are in relative agreement, but there are small differences here and there. For example, one group actually used the ICL to sort of constrain their lens model. So definitely I would go through the literature and see that there's a lot of other ones. Check out. Thank you all.
Is online. It's Hannah Yuka, who will speak about the intermediate mass black hole at redshift 5.55 with the NIRSpec IFS, which we haven't heard about yet today. So.
Hello, everyone. Good afternoon. Can you hear me okay?
Yep. Sounds good.
Thank you. Yeah, I'm very sorry that I cannot be here, but I'm showing you a picture that I took this morning in Cambridge in the UK, where I'm sitting at the moment. So this is similarly exciting to have all the snow here, like this fantastic conference. And I want to thank the organizers very much for giving me an opportunity to present some of our work here today. So I'll be talking about a low metallicity AGN at redshift 5.55, which we find in a star-forming region of the BPT. And this is work done in collaboration with the NIRSpec Galaxy Assembly IFS GTO team. And I'm listing the team members here on the slide, highlighting in bold a couple of people that are also talking at this conference. And of course, more people are in the room with you, including also our chair, Stefan. And before I go into the results of this particular object, I just want to give a very brief overview of the IFS GTO survey. So this is a program led by Santiago Arribas and Roberto Maiolino. And we are targeting with the IFU 42 galaxies at redshift 3 to 9. And there are various star-forming galaxies, AGN, also high redshift quasars in this program. And we target them with both high resolution and low resolution for most of the objects. And later during this meeting, Madeleine Marshall and Bruno Rodriguez del Pino will also present some of the results from within this program. Now, I want to talk about a source at redshift about 5.6, as I said, which has already received a lot of attention in the literature, has been studied in the past decade by a couple of people, and I'm listing some references here at the bottom. And this source is a very compact galaxy, as you can see in the HST image here to the left, showing roughly a cutout, which is the NIRSpec field of view of the IFS. So this is just a fraction of a kiloparsec or so. It's a little bit uncertain what the exact size is. Appears to be massive in star forming. And it has been targeted in particular with FORCE2 and the VMO spectrograph at the VLT. And so in this middle panel, I'm showing here one of these spectra that were taken targeting the rest frame UV. And here people found with the Lyman alpha line that there's also an outflow in the source of about 400 to 500 kilometers per second. And now to put this into context of what we are observing with NearSpec, if you look at this SED here to the right from the same publication, the rest frame UV is indicated here. And now with NearSpec, we are targeting what is the rest frame optical. So we're covering about 3 to 5 microns here. And so we will see the O3 and the H alpha emission. And so this is what it looks like. In this top, a smaller panel, I'm showing, let's say, a normal view of the spectrum. And you can clearly see the narrow emission of H beta, O3, and H alpha. And you might be able to see also this very broad line base, which is actually a broad line region in H alpha and in H beta. And this really pops up if we change the y-axis here to a log scale, which I've done in this larger panel that you can see at the bottom. And now again, you see all of these narrow lines, but really these broad line regions in H alpha and H beta pop up. In addition, we see several helium lines. We detect actually helium-2 and several helium-1 lines, and they all also show this BLR region. We see some other interesting features in the spectrum. For instance, we have another high ionization line detected here with forbidden argon-4, and we also see in the line base of the O3 indication for an outflow. So this is really extremely rich spectral information that we have here, and it's really fantastic. Now with the IFS, of course, we can also look at the spatial projection of these emission line features. And so here I just want to show a couple of plots for this. So in the top here we have a velocity field of the narrow O3 and of the narrow H alpha. And what you can see here is that these kinematic features that we see are very consistent in both of these lines. We see indication for a shallow velocity gradient of about 70 kilometers per second. But what you can also appreciate, of course, is this very specific shape of the emission that we see here. And as you might already have guessed, this is, of course, just emphasizing again how compact this source is. What we see here is, in fact, the imprint of the PSF onto the source. Okay, so this is barely resolved. We can also look at the outflow, and here we see that this is redshifted with about 100 kilometers per second, and we can use this also to calculate mass loading factors and things like this. But in the talk, I want to focus on some other things that we can do with the spectrum. So first of all, I want to focus on this BLR emission that we see in the Balmer and in the helium lines, and what we can do with this. So here's a zoom in with our best fit around the H alpha region. This is cut here just to highlight a little bit more these different emission features. And I'm also highlighting here the BLR region in purple. And we can use the Fourier max and the luminosity of this by using equations such as this one from Green and Ho to calculate what is the black hole mass from this BLR region. And if we do this, we find that it's about 10 to the 8 in the black hole mass. And this plot was shown already by Emma Curtis-Lake earlier today. We show here the black hole mass as a function of dynamical stellar mass, together with a couple of other redshift greater than 6 quasars by Izumi as these red dots, and in black, the local relation by Cormandy and Ho for black hole mass, bulge mass relations at local redshift 0. And now our source, which is here black hole mass 10 to the 8, has a dynamical mass which is in the range about 10 to the 9 to 10 to the 10. This is a little bit more uncertain due to the uncertainties on the size of the source, but it's in this regime. And with this appears to be, as was already pointed out earlier, a little bit overly massive compared to this local relation. And we've seen this also for these other sources that Emma already showed today, at redshift 5.9 and 4.7 from the JWST survey, which have even lower black hole masses, but again, with their stellar mass appear to be way above this relation. And also Feige Wang earlier today talked about this. And there was a question for Emma that she passed on to me, so I just briefly want to comment on this, which was about is this indication that this relation between black hole mass and dynamical mass of stellar mass is evolving with redshift. And it's actually interesting that in the current cosmological simulations, there is not really an agreement about this. So there are some simulations that find an evolution in the sense that at early redshifts, the black holes are more massive, but also the other way around. And I think this is, of course, now one of the strengths that we will have with these type of surveys and these type of observations, that we will be able to populate really this regime with the JWST observations to statistically pin down if there's really an offset or if these are just particular sources. And then again, this will, of course, inform seeding prescriptions, but also black hole mass accretion prescriptions in these cosmological simulations, and hopefully help us to also constrain the theoretical approach for this. Now, with the spectral information that I showed you before, we can do even more things. So now I'm showing you here in the left a classical PPT diagram. So we have O3 OH beta as a function of N2 OH alpha, and this is now looking at the narrow features. And our source is indicated here by these two stars. The green star is calculating these ratios just on the narrow lines, while the blue star is also including what we see in the outflow to sort of bracket what we find for our source. And again, these other two shade sources that Emma also showed. And in the gray background, you see the local population. So we have star-forming galaxies in HEN, and they are in the local universe separated roughly by these lines, by these from Kaufman and Cooley that I indicated here. So what you can appreciate here is that our source is now in the star-forming regime of this redshift 0 diagram, while we know that it's an HEN from the broadline region and the very strong helium lines. However, this is actually not unexpected, and it has been suggested by theoretical modeling work already that this could happen for low metallicity sources in the early universe. And now here I'm overplotting a couple of models. These are in particular by Nakajima and Maiolino, but several people have worked on this and finding similar results, and Stéphane Chalot, our chair, is involved in a lot of this work as well. And what these colored points now show, these stars and crosses are HEN models, and the different colors show different metallicities. So red is higher metallicity and green is lower metallicity. So indeed, our source is compatible with sort of a low metallicity HEN based on these models. But the other thing that we can see here is that these circles, which are evolved galaxies in this theoretical model, occupy a very similar region in the BPT. So this shows us that for these low metallicity sources at high redshift, the BPT cannot be used anymore as can be done in the local universe to distinguish star forming in HEN galaxies. And a very similar picture is if we look at a corresponding diagram just utilizing the S2 doublet instead of the N2 doublet again. Our source is in the star-forming regime, and we have here a mixture from theoretical predictions of low metallicity HEN and star-forming galaxies. However, we have even more spectral features for the source as I showed you, and in particular we have the helium-2 line, and this indeed can be used to still characterize these low metallicity sources. So again here I'm showing you a line ratio diagnostic, and this is the equivalent width of helium-2 versus helium-2 over H beta. Again, the colored symbols show these models from Nakajima and Maiolino, and what you can see here is that our source is consistent with their model, which has a relatively high accretion disk temperature. It might be even a little bit higher than what is explored in these models. And what you can also see here is that now these different HEN models are very far away from these evolved galaxy models. So this could really be a diagram where we can now distinguish HEN and star-forming galaxies also at high redshift. And another interesting diagram to help with this, I want to show you here on the right-hand side. So this is helium-2 over H beta, the function of nitrogen over H alpha. And in the local universe, again, this was postulated to have an even better distinguisher between the star-forming galaxies and the HEN, which is indicated here by this dotted line. And you can see that, again, our galaxies are here now on top of these HEN models, but also that the models for galaxies are very much further down here. And this is very interesting because this tells us that this diagram might also be used to classify star-forming galaxies and AGN galaxies at high redshift. And these are not washed out, so to say, but possibly that this dotted line will evolve as a function of redshift, basically moving down here. And so with this, in particular, this helium-2 line, we can still use now these theoretical prescriptions to distinguish what is the main ionization source in these galaxies. And this is basically all that I wanted to talk to you about today. So I've shown you some results from this galaxy GS3073, which has an active galactic nucleus, which we can very clearly see in the broadline region. And we can use this also to measure the black hole mass, which is about 10 to the 8. And while this is sort of at the lower mass end of known high redshift black holes, it still appears to be overly massive for its host galaxy dynamical mass. We've also shown that empirically, indeed, these galaxies now, this AGN moves into the star-forming region of the local BPT. However, by using other diagnostics, particularly involving the helium-2 line, we have empirically shown that this can still be used to distinguish AGN and star-forming galaxies, also for low metallicity systems in the early universe. And what is very exciting, of course, that with JWST and programs such as JADES, we will see data for many more high redshift AGN, and this will allow us to put statistical characterizations on their black hole masses, but also the line ratios, and for instance, to explore, as I said before, if there is a redshift evolution of this black hole mass stellar mass relation. And also in the IFS program, we have another 13 AGN and 6 quasars, for which we will then also be able to do spatially resolved analysis in addition to just an integrated spectrum and emission line modeling. And Emma has talked about this already. Madeleine Marshall later in this meeting will also talk more about some of the results. And of course, we don't only have AGN, we also have star-forming galaxies. And Bruno Rodriguez del Pino will present some results later in the meeting about this. Thank you very much.
Thank you, Hannah. There's time for 1 or 2 quick questions. Yes.
It was very nice work. Quick comment and question. So you said that the BPT diagram is hard to use for low metallicity things in the high redshift universe, but we also find it is hard to use for low metallicity things in the low redshift universe. Santosh Harish was looking for black holes in green peas with other diagnostics because we find you can't do it with the BPT. And the question I had is the scatter in the black hole mass bulge mass relation, how does that compare in the low redshift universe with what I'm seeing in the plot at the top right corner of your conclusions slide here? So, I mean, I see a lot of scatter at redshift 6. Is the low redshift scatter less?
Yeah, thanks very much for the comment and the question. Thanks for the comment. That's, of course, a very good addition that I should have noted. Thanks very much for adding this. For the question about the scatter, so the scatter that is shown in the diagram here is from the local relation. And as you pointed out, it appears to be that in these red data points that are the redshift greater than 6 quasars, the scatter appears to be much larger. And I think to some sense, of course, this is related to uncertainties also in the measurements that we have for these high redshift sources. And again, here, I think just with statistics, for instance, through JADES, we will be able to constrain also what is in scatter and maybe distinguish between measurement uncertainties and intrinsic scatter for these high redshift sources. The scatter that is shown for the local relation here is intrinsic scatter, and so clearly there seems to be a difference in what we see for the high redshift sources, but again, could also be partly measurement uncertainties.
Okay, so last question because we are running out of time. Yeah.
Yeah, thanks. Amazing spectra. I've seen like redshift 2 ones from MOSFET, and this is crazy to see these spectra. But my question is also more into the BPT diagram, because once you go from the forbidden O3 line to the recombination helium-2, it has been shown in the past, like by us and other people, that helium-2 is a little bit more complicated because of X-ray binaries and strip stars and shocks and stuff. Do you guys incorporate that as well to see if there's some degeneracies between AGN and stuff once you move the BPT diagram to helium-2?
that sounds like it's certainly interesting to explore. So I would be interested to look into in the work that you reference. Maybe you can put something in the Slack. So this particular source does not show up in X-rays at all. So I'm not sure whether this would be something that would show up in what you mentioned. I didn't catch completely what you mentioned about the X-rays.
I'll put that in the Slack. Maybe it is mostly stellar population things rather than X-ray detections itself.
Okay, great. Thanks.
Okay, thank you very much again, Hannah, and excuse me for misspelling your talk before. Okay, so the last presentation today is also remotely, and this is from Brent Robertson, who will speak about the first results on the earliest galaxies from the JADES NIRCam program. Brent, you...
I'm having difficulty sharing my slides via Blue Jeans here. Just a moment.
Okay, looks good. Yeah. So we don't hear you. We don't hear you. Are you muted?
I'm so sorry about that. I appreciate.
There you are.
Patience.
Okay, you're back.
Okay. Thank you for letting me give a talk here. I'm sorry I'm not there with you. I'm exiting COVID protocols today, so I'm a little bit under the weather still. Today, I'm really lucky to be able to tell you about all of the amazing work that's happening in the JADES collaboration, although today, really, I'm just going to focus on this most recent paper. So as you've heard, from Emma Curtis Lake's wonderful talk earlier today, we've discovered some very high redshift galaxies that we've been able to confirm with NIRSpec that really are at extremely high redshifts, and also confirm some previously known objects that were discovered with HST. So I'm going to tell you a little bit about how those galaxies were identified or how we've learned more about them, and to tell you a little bit more about JADES. I really want to thank everyone in JADES, amazing people. There are lots of people in the room with you there, but especially on this paper, Sancho Takela and Ben Johnson worked very closely with me, and also Kevin Hainline was instrumental. And Lily Whitler, Daniel Eisenstein, Ryan Ensley, Marcia, Riki Dan Stark. There's a huge number of people, many of them are listed here. So thank you for all of your efforts. So you may have seen this, this plot before. We are very lucky to live in an interesting and exciting universe. And usually when I give a talk about reionization, I'm usually talking about redshift of 7, but now I get to multiply that by a factor of 2 roughly, and tell you about the even more distant universe. So today, we're going to be talking about how can we confirm these distant galaxies close to cosmic dawn. And to tell you a little bit about how we're trying to infer their properties, I think people are roughly familiar with the idea of how you might go about looking for them. I'll say a little bit more, but how do we then say anything else about them other than they're out there? So there's been a ton of progress today. We've heard just an amazing talk, and congratulations to the organizers of this conference for really putting together a list of talks that have been remarkable. Some of the earliest data.
So are you moving slides? Because we are only seeing always the same slide here. Oh no. My slides will connect.
Are those galaxies really as distant as they appear?
Okay. Yes. Hold on. Can you hear us?
Yes. Am I frozen?
Yeah, no, because your slides don't change actually. We are only always viewing the same slide.
Oh, that is not the way it appears here in Santa Cruz.
Okay.
So, you know, why don't I do the following thing? Let's see if there's anything I can do about that.
The one we're seeing is the one with the paper authors. Yeah.
All right, let me try. Oh my God. Well,
okay,
can
that's
you see
okay.
this?
Progress today.
Okay, let me just, you know, you've seen this before. No one needs to see that again. Let me just say, do you see this? Yeah?
Yes, we do. Yeah. Sears at JWST 1345.
Well, you know, this reflects what a challenge it's been to find these high redshift candidates. You know, you'll have to trust me that we're doing a better job finding the galaxies than flipping through our slide deck. So just very quickly, you know, we have exposures now with JADES in Good South. We're also going to come back and look at Goods North. We're also going to look at Good South. We have 9-band imaging with JWST alone from JADES. There are additional imaging programs, the UDF medium band in Good South. There's also fresco data over a large amount of the field. So some of the objects that I'll be talking about, they actually have 14-band near-cam photometry, which is really amazing, and like 24 bands from space that we can look at because all of the wonderful HST imagery is also available to us. There are exposures of something like 7 to 17 hours, depending on the filter that we're looking at, and you know the depths are 30 AB magnitude roughly. In a given, you know, aperture. Of course, if you change the aperture, you get a different answer. You know, this is a really exciting data set, and you know, eventually these data will become public, and you know, it'll be a community resource for many years. So that's exciting. So here's a multi-band image, color image that I made of Good South, or imaging in Good South. I made the PNG here. So, you know, we have a custom reduction. Mostly Sandro Tequila is the person who's been doing the mosaic. There's a huge number of corrections and adaptations that we've had to make. And, you know, these data are phenomenally challenging to deal with, much harder, I think, than HST is, in my opinion. What we do is we construct a signal-to-noise ratio images from detection image from our other images by stacking in an inverse variance weighted sense all of the red bands and then also F200W. And then we use the wonderful PhotoUtils techniques, you know, the Python package to build our own detection photometry pipeline. So what have we found? Well, there are 4 high redshift galaxy candidates that we picked out of the near-cam imaging. So we tried to pick them out in a way, you know, we were treating all the galaxies roughly in the same way. And, you know, we didn't pick galaxies all over the field. We only picked galaxies that we had a hope of putting near spec slits on. So, so it's a restricted, not a complete sample here. So I just want to be clear about that. And you can refer back to Emma's paper about some of the other details regarding the spectra. Kevin Hainline wrote a very nice paper where he showed how you can efficiently select out some of these high redshift galaxies as F115 or F150W dropout techniques, and that's basically the techniques that we've been using. Kevin's been leading a lot of that within JADES. 2 of the lower redshift galaxies were known for some time, for a decade, from Richard Bowens, Garth Illingworth, my colleague there, esteemed colleague, is you know, discovered some of these galaxies, and then Richard Ellis, who's also there. And I and Jim Dunlop, Ross McClure, a host of other people with UDF-12, we had ultra-deep HST observations and an additional filter and deepen the Y-band data. And so the redshift 11.58 or something galaxy, we actually thought the photometric redshift was at 11.9, and this was something where we didn't believe it. You know, we didn't want to say we believed it publicly, but so anyway, so you know, that is now with additional near-cam data in the medium survey, Richard Bowens and Garth and others then you know, have a similar photo Z. So there was some good reason to think that these galaxies might be at high redshift, but of course, you know, it needs to be confirmation. They're not galaxies, they're candidates until we can get a chance to confirm them. And if you want to look at what the photometric redshift distributions from NIRCam are, here they are, and you can see the photometric redshifts and the spectroscopic redshifts are in good agreement with one another, so that's comforting. Emma gave a very nice talk earlier today. She showed this in the NIRSpec data. For the purposes of what I'll be talking about, we adopt their spectroscopic redshifts. We're not using the spectra and other ways to infer properties of the galaxies. We do that purely based on the photometry, assuming the spectroscopic redshift. So this is kind of what our analysis looks like. This is for one of the galaxies, the one at redshift 12.63. We actually have the multiband imaging. We take out thumbnail, and then we forward model using Ben Johnson's ForceFo code the properties of galaxies in a small thumbnail. So we can vary the size and the luminosity and the shape of those galaxies, and do that for all of the galaxies and look at the various covariances between the properties of those objects, so we can really understand if there's another galaxy in that little field that might be affecting the photometry, what's happening. Overall, we get good agreement between doing that and circular aperture photometry if we use a small aperture. So that is in itself comforting. And then we can fit SED models using Prospector and other code that Ben Johnson wrote to try to infer what the stellar population properties are given the photometry that we see in the spectroscopic redshift that Emma and the NIRSpec team have. One of the nice things about using ForceFo, of course, is that we actually, since we do a forward model, we have some sense of what the intrinsic size and the intrinsic shape, the intrinsic light profile of these galaxies are. What's really interesting, some of these galaxies are extraordinarily small. They're not resolved. We've actually done similar modeling for brown dwarfs of similar luminosities in our field. And so we know that, yeah, indeed, we're not getting that wrong if we say that they're unresolved. They're pretty small. So we've done that check. Some of the galaxies are, though, resolved or slightly resolved. They're only a couple of hundred parsecs across, which is remarkable. We heard some of that, how remarkable that is from Dan Coe earlier today. The Sirsic profile indices of these objects are less than 2. So they're consistent with an exponential profile, but I don't want to say much more than that. It's very difficult to say much when they're so small. So, you know, we fit these, here are the SEDs of all the galaxies. Sandro Tekello ran these SED models, and we can infer their properties. And I'll show you, you know, people are always wondering, how well do you know these properties? Well, we vary them all against one another using Monte Carlo techniques, and that allows for us to understand what the underlying covariances are and what the constraints are, given parameters like the star formation rate, the specific star, the stellar mass, you know, we do a non-parametric fit to those. We've also done parametric fits. We've also tried a host of other models. So, you know, we have a good sense of what the properties of these galaxies are, given the constraints of the data, which, you know, are still, they're still very faint. We find typical stellar masses of somewhere in the range of 10 to the 8 to 10 to the 9 solar masses in stars, star formation rates of order solar mass a year, and ages, half mass stellar ages of less than about. That's all I wanted to say today. I'm very sorry about the technical difficulties, but I'm glad you stuck with it. Please enjoy your cocktails, and I'll be happy to take any questions you may have. Thank you very much for your time.
Thanks, Brian. There are question there, yes.
So just a quick question, putting together two of the numbers from your last slide pretty much. If you have a star formation rate of order a solar mass per year and a mass of 10 to the 8 to 10 to the 9 solar masses, you don't have time to make 10 to the 9 solar masses at that star formation rate. Was it faster in the past, or did I mishear something?
Yeah, so that is correct. So that particular galaxy that you're talking about, the one that has the higher mass, that's the one that's at 11.6. So there's something like 400 something solar masses a year, and that's correct. So the star formation rates that I quoted you are averaged over the last 30 million years. We did that consistently because higher redshift galaxies are somewhat younger than that one. That one is a little bit older, a little bit more.
Yes,
Hi,
Dan,
hi, Brant. Dan Coe. Sorry we're missing you here, and congrats to you and Em and everyone on these exciting results. I was wondering if there were other candidates at similar redshifts or higher that you maybe got spectra of and didn't pan out.
I don't want to comment too much about this because it's an active, ongoing piece of research for other people on our team. I will say that there are other high redshift candidates, and certainly there are other galaxies that spectra have been acquired for.
Okay, great, thanks.
Yeah, let me just say, at a host of redshifts, let me qualify that.
Okay, so if there are,
Stefan, do you want to say more? I don't know.
No, I won't. Yeah. If there are no more questions, I guess this concludes this session. Let's thank Brant and the whole speakers this afternoon again. Thank you.
Thank you all for a great first day. You have a 7-minute break, and then I hope you'll all enjoy it. Join us for a reception over in the cafe sponsored by Aura. Celebrate this great mission and everything. So see you soon. Sorry for all of those online.